So chapter 4 is all about calculations and chemical equations. We're first going to learn how to calculate the molar mass of a chemical equation. It's also called formula mass, sometimes molecular weight. So in order to do this, we're going to take the sum of the atomic masses of all the atoms represented. So the only thing you need to calculate molar mass is the chemical formula. So as you can see, I have some examples of chemical formulas here. H2O, CuCl2, C6H6. So what these subscripts are telling us are how many atoms of that element are present in the chemical compound. So the subscript gives us the numbers of each atom present. So we're going to use that number, that subscript, in conjunction with the atomic mass that we can find on the periodic table to calculate the molar mass of the chemical formula. So let's look at an example. In this example, we have the chemical formula of CHCl3. So to calculate the molar mass of that compound, we're going to make a list of each element present, in this case, carbon, hydrogen, chlorine. We are then going to write next to each of those elements how many of each element are present. So for carbon, there is no number after carbon, so we assume that there's just one atom of carbon. The same goes for hydrogen. As for chlorine, there is a subscript of 3 after the chlorine, so that means there are 3 atoms of chlorine present. The next column, we are going to look up each of those elements on the periodic table and figure out what their atomic mass is. So for carbon, it is 12.01, hydrogen 1.008, and then chlorine 35.45. Notice we are multiplying across the number of atoms by the atomic mass for each element present, and then adding those totals together to get the total molecular mass of the compound. When we calculate the molar mass of the compound, the units are grams per mole. This is going to help us do conversions later when we need to convert between grams and moles of a substance. So let's look at what a mole is, define it using Avogadro's number. So a mole is just the SI unit for the amount of a substance. It was devised by chemists so that we can count how many particles are present in a certain amount. For instance, if I had 5 grams of copper, using Avogadro's number, I could figure out exactly how many atoms of copper were present in that 5 grams. We do this by defining the mole by Avogadro's number, which is 1 mole is going to be equal to 6.022 times 10 to the 23rd. Notice we have the word particles after that giant number. Okay, notice that 10 to the 23rd, that's saying we take this decimal point and we are moving it 23 times to the right. So it's a very, very large number. Now the word particles is present because particles can actually be atoms, molecules, and formula units. It just depends upon what we're talking about. So if we are talking about an element, for instance, that word particles becomes atoms, because elements are made up of atoms. If we are talking about a covalent compound, the term particles is going to change to molecules. If we are talking about an ionic compound, the term particles will change into formula units. So let's look at how we're going to use this in a calculation. Now, it looks a little scary because it's such a big number. So I wanted to apply it because this number, this 1 mole is equal to 6.022 times 10 to the 23rd, is actually very similar to the word dozen. Okay, so what does dozen mean? So let's look at that. Dozen means 12, 12 of something. Now dozen can be applied to several different things. It doesn't just have to be applied to eggs, because that's usually how we think it. I have a dozen eggs. What does that mean? I have 12 eggs. You can also apply it though to pencils. If you say I have a dozen pencils, you have 12 pencils. Dozen donuts, 12 donuts. Okay, so we're going to use this definition of what dozen means in our calculations. So for example, if we want to calculate how many eggs are in 3 dozen, What we're going to do is we're going to take the number 3 and we're going to multiply it by what the word dozen means. And what the word dozen means is 12. So we're simply taking 3 times 12. And what that tells us is how many eggs are in 3 dozen? The calculation gives us 36 eggs. Now we can apply it the same way, but using Avogadro's number. So in the next question, how many atoms are in 3 moles? So in order to figure that out, all we're going to do is take that number 3 and then multiply it by what the word moles means. And what does moles mean? 6.022 times 10 to the 23rd. So multiplying those by each other will give us the number of atoms present in 3 moles. Okay, so looking at the mole once again, how it's equal to 6.022 times 10 to the 23 entities. Now remember, entities can be atoms, molecules, or formula units. It all depends upon what you're looking at. Are you looking at elements? Well, then it's atom. Are you looking at molecules? Well, then it's a covalent compound. Formula units then would be an ionic compound. So this is how we're going to apply these calculations. Just a quick reminder, giving more specific examples in changing the word entities. If I have 1 mole of carbon, since carbon's an element, if I was going to calculate that using Avogadro's number, it would be atoms. So carbon's an element, so atoms would be what entities becomes. For 1 mole of water this time. Now looking at water, it's a covalent compound. It has 2 nonmetals present. 2 nonmetals, covalent compound, so entities becomes molecules. Last but not least, we have sodium chloride. What's sodium chloride? We have a metal and a nonmetal, so it must be ionic. So if it's ionic, formula units. Here's a quick flow chart of some of the calculations we're going to be using. Now this flowchart is not given to you on exams. However, it's going to help us initially figure out what steps we need to go through in order to convert from one thing to the next. So you'll notice from this flowchart that we go between mass, moles, and atoms or molecules. Okay, so notice we cannot get straight from mass to atoms. We're always going to have to go through the mole section first. Right, so to go between mass and moles, we're going to need the atomic or molar mass. So that's why we learned how to calculate it at the beginning of this chapter, because we're going to be using that to get between mass and moles. That's why the units on molar mass is grams per mole. We're going to use that as a conversion factor to go between grams and moles. To get now, look at the next step between moles and atoms. We are now using Avogadro's number, because Avogadro's number says 1 mole is equal to 6.022 times 10 to the 23rd atoms. So we're using Avogadro's number now as a conversion factor to go between moles and atoms. All right, so this calculation here, how many moles of water are in 35 grams of water? So in order to figure that out, let me go back to the previous slide. Oh, I guess I can't go back to the previous slide. So in order to figure that out, we need molar mass, because we just looked on the previous slide. We saw that if you had grams and you wanted to get to moles, you needed the molar mass to do that. So that's what this calculation here is showing. It's showing the calculation of the molar mass of water. 2 atoms of water, 1.008 being the molecular mass on the periodic table, and then 1 atom of oxygen with a mass of 16. So adding that together, we get the total molar mass. Notice the units are grams per mole, so this is going to be a conversion factor. Start with what's given in the problem, the 35 grams of water. Use the molar mass as a conversion factor, having grams on bottom to cancel, leaving you with just moles. And yes, this is the incorrect number of sig figs. So I want you to note that is my mistake. All right, let's look at the next one. How many molecules of I2 are in 40 grams of I2. So once again, we're starting at grams like in the previous problem. But notice this time we are going all the way to molecules. We said that we could not go from grams straight to molecules. So we need to go to moles first, like we did in the previous one, and then we'll go to molecules. So to do this, we need two pieces of information. To go from grams to moles, we're going to need the molar mass of I2. So we're going to have to calculate that just like we did in the previous problem with water. We are also going to need Avogadro's number, which is 1 mole is equal to 6.022 times 10 to the 23rd. The molar mass and Avogadro's number are going to be our two conversion factors that are going to convert that 40 grams all the way to molecules. So looking at the setup of the railroad tracks, you start with what's given in the problem, the 40 grams. This next step here, this is the molar mass of I2. Notice it's grams per mole. You put the gram portion on the bottom so that they cancel, and the moles on top. At this step, you are now in moles. So you then use Avogadro's number, putting the mole portion on the bottom so that moles and moles cancel, and the molecule portion on the top. So multiplying across and dividing what's on the bottom, and you get 9.48 times 10 to the 22. Now that times 10 to the 22, that's an important part of the number. That is saying that this is a very large number, that you have a lot of those molecules. So do not forget that times 10 to the 22. That's an important part. It's telling you it's a big number. All right, so let's look at mole ratios. Mole ratios, we've actually done this before already. We just haven't applied it in this way. So when we talked about chemical formulas before, we said that the subscripts after each element tells us how many atoms of that element are present. Okay. Well, it also tells us the ratio. So I could say, using this chemical formula, there are 6 atoms of carbon, 12 atoms of hydrogen, 6 atoms of oxygen. I can also say there are 6 moles of carbon, 12 moles of hydrogen, and 6 moles of oxygen. It applies in the same way as if they were atoms. Okay. So the subscripts are going to tell us what the ratio is. So it's a 6 to 12 to 6 ratio, or if you reduce it down, 1 to 2 to 1. So for every 1 mole of carbon I have, I need 2 moles of hydrogen and 1 mole of oxygen. All right, so how are we going to use this? Well, it's easy to figure out the mole ratio when you have 1 mole of the compound. So I'm looking at this first example here. If I have 1 mole of that entire compound, then I'm just using the subscripts to figure out how many atoms of each element I need, right? So if I have 1 mole of that entire compound, that means I have 12 of carbon, because that's the subscript on carbon, 22 of hydrogen, and 11 of oxygen. Okay. Well, if I needed more than 1 mole, so now say I need 2 moles of that compound. Well, how do I figure out the moles of each element that I need? What you're doing is you're taking the coefficient, so this number 2, and you're multiplying it by each subscript in that chemical formula. So 2 times 12 will tell me that I need 24 moles of carbon. 2 times 22 will tell me that I need 44 moles of hydrogen. 2 times 11 tells me I need 22 moles of oxygen. All right, well, what if I need less than 2 moles? What if I need 0.2? You do it the same way we did the previous one. You take this coefficient, this 0.2, and you're going to multiply it by each subscript to figure out how many moles you need of each element present in that chemical formula. So taking the 0.2, multiplying it by 12 will help you figure out how many moles of carbon you need. Taking that 0.2, multiplying it by 22 to figure out hydrogens gives you 4.4. Last but not least, that 0.2 times 11 tells you how many oxygens. All right, there's an example problem down here that we did in class. Go ahead and try it again, get a little practice with that. Using 1.8 moles of the same compound, calculate the number of atoms. So remember, you're just taking this 1.8 moles and multiplying it by the subscript of each element present. All right, so these problems here, I'm going to try to post a video of me working these problems out on a whiteboard or a piece of paper. So stay tuned for that, and hopefully that will help you figure these problems out and be able to do the homework and some of these problems on your own. I'll also be posting some videos of other instructors, other YouTube videos converting from grams to moles. I already have some of those up, so those should help as well. All right, let's move on to chemical reactions. So what is a chemical reaction? A chemical reaction occurs when chemical bonds between atoms are broken or formed. All right, so basically you are breaking bonds and forming new ones. You're making new compounds. You are rearranging atoms, essentially. So chemical reactions contain two general components. First, the reactants. And what the reactants are is they're the components that are mixed together. It's what you put in the flask. So if you're going to do a chemical reaction, it's what you're tossing in. What the products are then is what you're getting out of the flask when you're done. What was made? What's the end, the final product? When we represent chemical reactions on paper, we have the reactants always on the left-hand side, and then an arrow pointing to the products on the right-hand side. So here's an example of a chemical equation, how we represent a chemical reaction. So in this chemical equation, we have 4 aluminums reacting with 3 oxygen molecules to form aluminum oxide. Okay, so the reactants in this case are aluminum and oxygen because they are on the left side of the equation, and the arrow is pointing to the product, which is aluminum oxide in this case. So you can sort of think of that arrow as an equal sign. I'm adding these two and it's equaling the product. Okay. Some other key points of a chemical equation is you'll notice that there are these coefficients in front of each element or compound. So those coefficients are going to be very important when we talk about balancing equations. Those coefficients are making sure the atom count is the same on both sides. And we'll get into that a little bit more in a moment here. One other thing I did want to point out, however, is that notice there's also little letters after each element or compound. Okay, so what these letters are for is they're telling us what form, what physical phase that particular element or compound is in. So for aluminum, it has an S after it. What that's saying is it's solid. They took a solid piece of aluminum and put it in the flask. Oxygen has a G. That is just saying that it was a gas. So they pumped oxygen gas into the flask. When the reaction was complete, the product, aluminum oxide, has an S by it, so it was a solid. Other phases you might see are liquids. That will have an L by it. Water is often going to be in the form of a liquid. You'll also see aqueous, which will be an AQ. That is simply a solid that was dissolved in water. Okay, so it's not a liquid because it's not pure because it's two components mixed together. That would be aqueous. So let's look a little bit more at these coefficients that I mentioned previously. They are now in red. So those coefficients are helping us to make sure that there are the same atom counts on both sides of the equation. So why do we need the same atom count on both sides of the equation? We need it because of the law of conservation of matter. And what the law of conservation of matter says is that the atom count must be the same on both sides. Energy cannot be created or destroyed. Well, neither can atoms. Okay, so if whatever I put in the flask, I need that same amount of stuff coming out of the flask. So that's what the atom count is saying here. So how do you figure out the atom count? Well, you take the coefficient and you multiply it by the subscript. So I have it color-coded here so we can see it a little bit better. So notice coefficients are in red. The subscripts are in yellow. Okay, so On the reactant side, I am going to calculate how many aluminums I have, how many oxygens I have. However many aluminums I have on the reactant side, I need to have the same amount on the product side. Same with the oxygens. So let's count. For aluminum, I have 4 of them. For oxygen, I'm going to take that coefficient of 3 and I'm going to multiply it by that subscript of 2. So 3 times 2 tells me I have 6 total oxygens on the reactant side. Now I'm going to go to the product side. I have a coefficient of 2. So I'm going to take that and I'm going to multiply it by the subscript of 2 to give me a total of 4 aluminums. So that checks out. 4 aluminums on the reactant side, 4 on the product side. Good there. Now I'm going to do it again for the oxygen. So this coefficient of 2, it applies to every element in that compound. So it's going to apply to aluminum. It's also going to apply to the oxygen. So I'm taking 2 times 3 in this case to get a total of 6 oxygens. So atom count is the same on both sides, 4 aluminums and 6 oxygens. When we balance our own equations, what we're going to be doing is we're going to be changing the coefficients. Those numbers in red, those are the numbers we control, those are the numbers we can change. We cannot change the subscripts, the numbers in yellow. Those have to stay the same. If we change the subscripts, we are changing the chemical compound. So only the coefficients can be used or changed to balance the reaction. Subscripts cannot be changed. All right, so some other equation details before we look at some next topic is we discussed this previously, the small letters present after each element or compound indicates the phase. So we have solid, gas, liquid, and then aqueous. So in the example down here, sodium chloride being table salt, that's a solid, right? I said water is a liquid at room temperature. So if we take a solid table salt and we put it in water, what happens? It dissolves, okay? And when it dissolves, we have now made an aqueous solution because it is a mixture of solid sodium chloride that has been dissolved in water. All right. So let's look at some different types of synthesis or combination reactions. We have 5 different types of reactions that we're going to be learning, and you need to be able to recognize these reactions and label them correctly. Okay, so the first type we're looking at is synthesis. It is also called a combination reaction. It is called this because you take 2 things, 2 reactants, you're adding them together to make one product. Okay, so the example that I have here is taking H2 gas, O2 gas, combining them in a combination reaction to synthesize water. So the next type we're going to look at is a decomposition reaction. And this is kind of the opposite of a combination reaction because in this case, on the reactant side, we have one compound and that compound is breaking apart. It's decomposing into 2 separate products. Okay, so with synthesis, we had 2 things on the reactant side combining to form one thing. Well, with decomp, we have one reactant compound breaking apart into 2 products. Right, so the example shown here is nickel 3 oxide breaking apart to form nickel and oxygen, so into its elemental form. The other examples that I have down here are some different acids that are decomposing in decomposition reactions. Notice in all of them we have one reactant, and that reactant is breaking apart and decomposing into 2 products. Okay, so that's how you can identify these as decomp, because I have just one reactant breaking apart into 2 products. In this case, these acids are all decomposing into water and their counterparts. The next type of reaction is a single displacement reaction. With a single displacement reaction, we have element or ion basically switching spots with a compound. So how do you recognize this as a single displacement? Well, you have a metal by itself in its elemental form, and it is going to switch places with another metal that's in a compound. Okay, so in this example down here, we have zinc by itself in its elemental form, and it's going to kick copper out of its spot so that zinc is now with SO4 in a compound, and copper ends up by itself. So it's replacing or displacing one element for another. Now, in the case of single displacement, remember that zinc is going to take the place of copper. Zinc will never take the place of SO4 because we always want a cation with an anion. We always want a positive with a negative. We want the metal with the polyatomic. What I mean by that is you're not going to see zinc and copper forming a bond together because they're both metals, they're both cations, both of them have positive charges, and positives, likes do not attract, likes repel. Okay, we need opposites attracting here. You're going to have to be able to predict products of some of these reactions, so that's why I'm pointing that out here. So let's look at the next example. So we have aluminum by itself. So think of that as being the A in this diagram up here. And what that A, that aluminum, is going to do is it's going to go over and it's going to kick out B. So in this case, B would be copper or sulfate. What is it going to take the place of? It's going to take the place of copper because aluminum's a metal, so it's going to take the place of another metal. So now, on the product side, we have aluminum with the sulfate and copper by itself. Okay. Now, what is the driving force of these reactions? Well, we said a metal always replaces another metal. So these A and B that we have up here, okay, these are usually metals. Not always, but usually. C generally represents the nonmetal or the polyatomic. What drives these reactions is the more active metal replaces the less active one. And we're not going to get too much into reactivities of metals, but I do want you to be able to know the reason behind it. Okay, you don't have to memorize the table of the reactivities. Double displacement reaction. So what do we have here? In this case, it's very similar to single displacement because we're switching places. But in this type of reaction, instead of having an element or a metal alone by itself, we have two compounds reacting with each other. Okay, so there's no one by themselves. So we have two compounds on the reactant side, and we have two compounds on the product side. So that's how you can identify it as double replacement. Two compounds switching partners forming two new compounds. So in this case, we have calcium bromide and silver 1 nitrate. So calcium bromide, the calcium is going to switch partners with the silver because the metals switch with the metals. You're not going to see the two metals together, so they're going to switch partners. So calcium is going to steal silver's partner, the NO3, so that on the product side, we have calcium nitrate. The silver now isn't going to be with nitrate anymore on the product side. Instead, silver is going to be with bromine. So we have silver 1 bromide as a product. Now, the driving force for these reactions is the formation of a solid. So if you'll notice these little symbols down here, right, they tell us the physical state. We have aqueous for the calcium bromide, aqueous for the silver nitrate, and then over on the product side, notice we have one aqueous, calcium nitrate, but the other one's a solid, because the formation of a solid is what helps drive these reactions forward. Well, how do we figure out if a solid forms or not? Well, these reactions, since they form a solid, they're often referred to as precipitation reactions. Okay, so what is a precipitation reaction? It's when you combine two liquids and you get out a solid. So what a precipitate is just another word for a solid. So if I say, okay, I mixed these things together and out came a precipitate, what I'm saying is out came a solid. I saw a solid form. All right, so we're going to use solubility tables to predict if a product will form. Because when you do these reactions, you're not going to be given this S here and this aqueous here. You're going to have to figure those out using solubility tables. So these are the tables that we are going to be using to predict if a compound will form a solid and if a compound will not form a solid. So you'll notice we see the words soluble and insoluble. Okay, so what soluble means is the substance is dissolved. So no solid formed. So if you hear the word soluble, that means it dissolved. The word insoluble then will mean that a solid or a precipitate has formed. All right, so how are we going to be applying these tables? What this table is saying, this top one, is that looking for these ions that are in the compounds, if any of these ions are present, they can be soluble, so they can dissolve. If they're with an exception over here, that means they will be insoluble. Let's apply and use it. We'll take a little closer look at this. Okay, so here is a picture of a reaction where we are mixing potassium iodide with lead 2 nitrate. And you'll notice you see this yellow foggy material forming. What that is it's a bright yellow precipitate. It's actually a solid. So we know that when we mix potassium iodide with lead 2 nitrate that a solid is going to form. Our job is to figure out what solid. So I have the reaction equation written down here. Reactants on the left-hand side, arrow pointing to the products. When I mix potassium iodide with lead 2 nitrate, I'm switching partners because it's a double replacement reaction. So potassium is going to take the place of lead. Lead is going to take the place of potassium. They're switching partners. So on the product side, I have lead 2 iodide and potassium nitrate. Now I'm going to use those solubility tables to figure out, is it lead that made that solid yellow precipitate, or is it potassium nitrate? So what we have on this slide is a little closer look on the molecular level of what's happening. So if you notice, I have the reactants over here on this side, and then I have my arrow pointing to products. So what happens when we take ionic compounds and we put them in water is they dissociate into their ions. We talked about this property with ionic compounds, how they break apart into the cations and the anions, and that's why they can have some conductivity. Okay, that's why they can conduct or have the possibility to conduct electrical currents, because they have these ions, these charged ions floating around in the water. So with potassium iodide, we have little potassium, little K+ ions, and we have little iodine, I- ions floating around. Now, what's nice about this is we have two aqueous solutions, aqueous just meaning that our solids were dissolved in water. And since those ions are now separated into their counterparts, it makes the reaction happen really quickly because we have all these ions just floating around. So when they bump into each other, they connect and form a new compound, essentially. So on the product side, we can see all the ions floating around there. So what we need to figure out is which ions are getting together and forming this yellow precipitate. Okay, so let's look at that solubility tables to figure that out. So what I want to do here is, here are our two possibilities that we were looking at on the previous reaction equation. We had lead 2 iodide as one of the products, and we had potassium nitrate as one of the products. So we're going to take these ions, find them on the table, and figure out if they are soluble, meaning dissolved, or if they are insoluble, meaning yes, precipitate formed. All right, so I'm going to start with my potassium nitrate. So to do this, I can either look for the potassium ion, K+, or I can look for the nitrate. It doesn't matter which one. Either one will give me the same results. So say I look for my potassium first. So what I do is I go over to the table and I find where K plus is. And what it tells me, the table says that K plus is going to be soluble. Now that means it can be soluble. It doesn't mean it's always going to be, because I need to follow this line over to where the exceptions are. But notice the exceptions in this column, there's none. So what that means is that potassium, K plus, is going to be soluble all the time with no exceptions. So that means it's always going to dissolve in water. It's never going to form a solid. So that tells me that KNO3 is definitely not going to form a solid, because it's going to be soluble no matter what. Now, if I had decided to find NO3 first instead, the anion portion of that same compound, right? Notice it's telling me that it can be soluble, and I'm going to follow over to the exceptions, and once again, no exceptions. So that means if I have a nitrate anion, it is going to be soluble in water all the time, no exceptions. Okay, so it's giving me the same answer, notice, no matter which ion I looked up on the table. So KNO3 is soluble. It's not going to be the solid. That means lead 2 iodide is probably going to be the solid, but let's look and make sure. So when I'm looking at this table, I can look up either the lead Pb 2+, or I can look up the iodine minus. Now when I look at this table, the iodine minus I can find a lot easier. So when I find that anion, it's telling me that it can be soluble. But now when I follow it over to the exceptions, it's saying iodine soluble unless it's with one of these 3 metals. Notice one of those 3 metals is lead 2. So that's saying that iodine, yes, it can be soluble unless it's with silver, lead, or mercury, and it is with lead. So the exceptions are telling us that a solid will form if it's with one of these guys. Iodine is with one of those guys, so lead 2 iodine is a solid. So we have solid for the lead 2 iodide, and then we'd put an AQ by the potassium nitrate because it's soluble all the time, no exceptions. Some other common reactions that we need to know are listed on this slide here. The one that I want you to focus on most is this combustion reaction at the top here. So what a combustion reaction is when we have a hydrocarbon, so a hydrocarbon being a compound with just carbon and hydrogen present, reacting with oxygen to form carbon dioxide and water. So what's special about this type of reaction is you're always going to have a hydrocarbon mixing with oxygen. Those are always going to be your reactants. So oxygen will always be one of your reactants. And your products are always going to be carbon dioxide and water. So if you see 2 products, carbon dioxide and water, you know it's a combustion reaction. So the reason I'm keep repeating this section is because you're going to need to be able to identify if a reaction is a combustion reaction. And the telltale signs of that are the products are carbon dioxide and water every time. Okay. The other reaction I have on this slide down below is iron and oxygen combining to form iron 3 oxide, which is rust. Okay, that one you won't have to memorize the reaction layout or be able to identify. So let's look down below at this last type of reaction. And this is an acids and bases reaction where we're seeing a proton transfer. Now I'm just introducing this reaction here now because we're going to look at this a lot closer in later chapters. But while we're talking about reaction equations, I just wanted you to see a quick example of that. So what we have happening here is we have an acid, in this case hydrochloric acid, HCl, a base, NaOH, sodium hydroxide, and when they react together, a neutralization of sorts happens because our products are going to be water and salt. right? So we'll explore this reaction in further depth in a later chapter. I just wanted to introduce the layout of it now. So out of these reactions, the one I really want you to remember is this combustion reaction here. Okay, remember that it is always a hydrocarbon reacting with oxygen, and products are always carbon dioxide and water. Stoichiometry. So notice it says board notes on this slide. This is not a topic that is easy to explain with PowerPoint slides. I have posted some videos of people explaining stoichiometry, and I will also be posting some videos of me working out stoichiometric problems. Okay, so I just want to give an overview definition of what stoichiometry is. So it's the calculations of reactants and products based off a balanced chemical reaction. Okay, so that's a official definition. So the reason that we have been learning how to balance equations, the reason that we have been looking at mole and mole ratios and calculating molar mass, all of this stuff is coming down to these types of problems. So we're going to be using balanced equations with coefficients to balance to make sure the atom counts are on the same side. And with these coefficients, we're going to further apply that to figure out the number of moles. So we're using mole ratios here. So in this chemical equation that I have, notice it's a combustion reaction. We just talked about that on the previous slide because we have a hydrocarbon with oxygen and the products are carbon dioxide and water. So these coefficients that are in front, and if there is no number in front, it's just we assume it's a 1. These represent the number of moles of each of those compounds. So if I were to rewrite this chemical equation and apply it to moles, I would be saying that there is 1 mole of CH4, and I'm adding 2 moles of oxygen to that to get out products 1 mole of carbon dioxide and 2 moles of H2O. Okay, so we're going to use these mole ratios, this balanced chemical reaction, in these stoichiometric calculations. Here are just a few examples of the types of problems we're going to be applying. So I know that word stoichiometry is a big word. What we're doing is we're taking all of our conversions that we've learned and we are just applying it to a chemical equation. We're using information from a balanced chemical equation to help us solve these problems, to help us go between grams of aluminum to moles of O2. Because note, so far, with all of the calculations we've done, we've been going grams of aluminum to molecules of aluminum. It's always the same element. We're talking about the same element. But when we have a chemical equation, we can go between aluminum and oxygen and even to products if we want, aluminum oxide, because of these coefficients, because of these balanced equations. So be on the lookout for a video that I'll be posting solving the problems that you see here and showing you exactly how we're going to apply chemical equations and stoichiometry to do these types of conversions, to go, for instance, between grams of aluminum all the way to moles of oxygen and back. So this is one of the last equations that calculations we're going to be using in this chapter. We're going to be taking theoretical yield and actual yield and calculating percent yield. So let's look at the definitions of theoretical and actual yield. So theoretical yield is how much product you should get according to the balanced chemical equation and how much starting material you used. We've actually done this in lab before, right? We calculate how much we should have made or how much we should have recovered. That's your theoretical yield, the maximum amount that you should be able to get out. Now that's different than your actual yield, because your actual yield is how much you did get out at the end of the experiment. And as we've all seen, you don't get it all back because there's some residue in a flask or something was spilled. There's a lot of human error there. So the actual yield and theoretical yield do differ And that's what this calculation is for, to figure out what percent do they differ. Okay. Some other definitions. We have limiting reagent and excess reagent. So what a limiting reagent is, it's the reagent in the smallest amount. Okay, and this is in moles, not in grams. Okay, so you need to compare mole amounts when you're trying to figure out limiting versus excess. So the limiting reagent is the one with the smallest amount of moles. And when this limiting reagent gets used up, the reaction is going to stop. The excess reagent is the reagent that is not the limiting reagent. So it's the one that you're throwing a ton into it. Okay, it's usually the cheaper of the two. So you're going to put a lot of the excess reagent in order to use up all of the limiting reagent. So excess reagent does not determine theoretical yield at all. It's the limiting reagent that's going to determine your theoretical yield, how much product you should get out. When you're done with the experiment, all of your limiting reagent should be used up, but you will have some remaining of the excess because you had excess of it in the reaction flask. I'll also be showing some calculations on how to calculate limiting reagent and figuring out theoretical yield. So be on the lookout for those videos as well. Mass percent of a solution. We've done this in lab as well when we did the sand and salt, silicon dioxide and sodium chloride, when we separated the two and we figured out the mass percent of silicon dioxide and the mass percent of sodium chloride. So here is just the calculation for it. So if you're figuring out the mass percent of something, so say it's silicon dioxide, you're going to take the mass of the component, the silicon dioxide, and divide it by the mass of the total solution. And since it's a percent, don't forget to multiply it by 100. Since we're talking about solution, I wanted to define what a solution is. So a solution is made up of a solute and a solvent. So say for instance, I take table salt and I dissolve it in water. One of those two components is the solute, the other component is the solvent. How do I know which is which? Well, let's look back up here at the definitions of solute and solvent. So a solute is the substance that is dissolved. It's the one present in lesser amount. So in that example, where I'm taking sodium chloride and I'm dissolving it in water to make a solution of salt water, my solute portion is going to be the sodium chloride, because the sodium chloride was the substance that was dissolved, and it's also the substance that in lesser amount. Now this leaves the solvent. The solvent in this case is going to be water. Definition of the solvent is the substance in which the solute is dissolved. Another way to easily identify the solvent is it's the one in greater amount. These definitions are going to come in very useful in later chapters when we talk about solutions, solutes, solvents, and even learn how to prepare some solutions in lab.